Take a look at this footage. We're watching a horse running through a field, rendered into a zebra with identical movement and background geometry. Historically, training an artificial intelligence to translate one visual domain into another required perfectly aligned training data. The system had to be fed paired examples to learn the translation rules. The real world rarely yields perfectly aligned pairs. You will almost never find a photo of a wild horse and a wild zebra standing in the exact same location, in the exact same posture, under identical lighting conditions. This gap in available data necessitates the CycleGAN architecture. It addresses the image-to-image translation problem without relying on strict one-to-one pairings. To understand how this system operates, we have to look at how it was built. We need to construct it from the ground up, starting with its earliest biological and mathematical origins. High-level neural architectures are built by stacking distinct solvable units. The initial blueprint for these models was the biological neuron. This diagram illustrates how the structure of a biological cell translates into a mathematical approximation. In the artificial model, dendrites become discrete numerical inputs, labeled X. Synaptic strength is represented by a learnable weight, labeled W. These inputs are gathered at the cell body and summed. If that combined total crosses a specific numerical threshold, the neuron fires. We can express this entire sequence in a single formula. Output equals the activation function applied to the weights times the inputs, plus a bias threshold. This single perceptron is the foundational block of modern neural networks. It takes raw numerical data and transforms it into a decision based on learned importance. A solitary perceptron is limited to solving strictly linear problems. It fails when confronted with the complex, entangled data distributions found in real-world scenarios. This table shows how we introduce nonlinearity. Activation functions, like the sigmoid or hyperbolic tangent, curve the output. This allows the network's logic to bend, rather than breaking along a rigid straight line. Look at these plots. By expanding the network to include 3 hidden neurons, it begins to map a rough shape. Expanding it to 20 neurons produces highly complex decision boundaries, capable of wrapping around intricate data clusters. To reach that precision, the network calculates a cost function, represented mathematically as E. This is the exact variance between the network's current guess and the actual target. This graph visualizes gradient descent. The network's objective is to minimize E, navigating down the slope of the error curve to find the lowest possible cost. The rate of descent is controlled by alpha, the learning rate, dictating the step size for weight updates. This diagram traces the method of backpropagation. The error signal travels in reverse, flowing from the output layer back through the network, adjusting every single weight connection based on its contribution to the final error. By embedding nonlinear nodes within a backpropagation loop, the system can continuously measure its own failure and self-correct to reach a specific target. Standard dense networks process data by flattening it into a one-dimensional line. When applied to an image, this flattening destroys all spatial context, pulling adjacent pixels apart. Convolutional neural networks, or CNNs, are designed to process visual data in its original two-dimensional grid, preserving the geometric relationship between the pixels. This visual represents a convolutional layer. Instead of analyzing the entire image at once, a small mathematical window, a filter, slides across pixels, extracting local features. Following the filters, pooling layers compress feature maps, shedding redundant data while maintaining the most critical patterns. This alternating process creates a hierarchy of representations. As this visualization shows, earliest layers identify distinct edges and simple lines. Middle layers combine these into repeating textures and geometric patterns. Deep layers assemble textures into recognizable, complex object parts, like a car wheel or a bird's eye. As the data pushes deeper, the network expands its feature extraction capacity. It typically increases from 32 filters to 64 to 128, mapping increasingly complex abstractions. Convolutional layers provide the system with a spatial understanding, identifying structural reality regardless of where an object is located in the frame. Recognizing an image is a matter of classification. Generating an entirely new, realistic image requires a different mathematical approach. This is the architecture of a generative adversarial network. It frames generation as a zero-sum game between two competing networks. On one side, the generator receives random mathematical noise, mapping that latent space into a synthetic data sample. On the other side is the discriminator. It receives both authentic data from the training set and the synthetic data from the generator. Its singular objective is to distinguish the real from the fake. They operate simultaneously on a minimax objective function. The discriminator seeks to maximize its accuracy, while the generator seeks to minimize the discriminator's success. If the discriminator successfully identifies a generated image as fake, the error signal backpropagates through the generator, forcing it to produce more realistic output. Conversely, if fooled, the discriminator receives its own error signal, updating its weights to become a more rigorous critic. This specific model relies heavily on the convolutional layers we just examined. Both the generator and discriminator utilize stacked spatial filters to understand and reconstruct visual patterns. The outcome of this continuous competition is a generator that learns to convert abstract mathematical noise into photorealistic outputs. GANs establish a self-improving loop of creation and critique. The network learns not by matching a static target, but by surviving an escalating adversarial race. So we have the components. Backpropagation provides the learning mechanism. Convolutional networks provide spatial awareness. GANs provide the generative engine. When we link these together, we achieve image-to-image translation. Early translation models, like Pix-to-Pix, perform accurately under strict conditions. A rough map outline is supplied as the input, and the model renders a photorealistic aerial image as the output. But it only functions because the training data consists of perfectly paired examples. Every sketch is directly mapped to a specific photograph. Which brings us back to the unaligned domains, the horses and the zebras. If a network translates a horse into a zebra, we have to verify it hasn't simply pasted a generic zebra over our image. We address this through cycle consistency. We require the network to take its generated zebra, translate it back into a horse, and measure the distance from our original input. This loop provides a mathematical incentive for structural consistency. By requiring the model to preserve the original geometry during the round-trip translation, it can successfully bridge the gap between unpaired datasets. By understanding these foundational blocks, we can see CycleGAN not as an opaque system, but as a specific architectural response to the scarcity of paired training data.